So I'm going to talk about joint work with Levent Alpog and Manjul Bhargava. So the topic is a kind of a natural question that comes up when you first take a course in algebraic number theory, or maybe when you first teach a course in algebraic number theory. And so this has to do with the notion of a monogenic number field. So K will be a number field. And I want to define what it means for K to be monogenic. So K is monogenic if OK, its ring of integers, can be generated as a ring by a single element. If OK is a Z algebra generated on one element alpha. And so of course, any number field is the primitive element theorem. It's generated as a Q algebra by a single element, but it's not necessarily, not in general true that integrally the ring of integers is generated by a single element, which is perhaps the first source of confusion for students when they see this definition and when they think about number fields. Maybe the second source of confusion is what happens when you start looking at examples. So let's say let's look at quadratic fields. So let's look at a quadratic field. K is Q adjoin root D. D is the discriminant of K. So in this case, K is always monogenic. So then in this case, you can always, the Gaussian integers are generated by I, the Eisenstein integers are generated by a root of unity, which has some fractions, some 1/2 integers in the coefficients. But in all cases, the ring of integers is just this. And so, OK, so K is monogenic when it's a quadratic field. And then you start moving up into higher degree number fields, cubic fields, quartic fields, and so on. Then you start seeing that this is not always true. And so Dedekind gave the first example, as far as I'm aware. There's some famous example of Dedekind of a cubic field that's not monogenic. And so I'll give kind of a general class of examples that falls under that for which the same proof works. So let's let K be a cubic field now. So degree 3 over Q. And let's assume that 2 splits completely in K. Okay, so what does that mean? That means that if I look p-adically or 2-adically, I tensor K with Q2, then it means that it factors as 3 products, three copies of the 2-adic numbers. Integrally, the same thing happens. So OK, let's do it over here. So OK tensor Z2 will be just 3 copies of the 2-adic integers. And I claim that this just cannot be Z2 monogenic. This is not equal or isomorphic to a ring that's generated by a single element over Z2. And it's easy to see this. What you observe is that this ring has 3 ring maps to the ring F2, the finite field with 2 elements, kill 2 copies of Z2, and then mod out by the maximal ideal in the 3rd copy, where this has at most 2 maps to F2. So they can't possibly be isomorphic. Now, if K were monogenic, then OK would be generated by a single element over Z, and then when you tensor with Z2, this would be generated by a single element over Z2, and so, but this can't happen. So this tells you that K is not monogenic. So, and it gives you a very large, some large class of examples also where that's true. Okay, but even amongst cubic fields, there are other kinds of cubic fields that are not monogenic, where 2 does not split completely. And in fact, if you look at people tabulated data, you look lots of cubic fields or higher degree number fields also, and they found that in general it was actually a rare thing to happen for once you're beyond degree 2 for a field, a number field, to be monogenic. And so there's, I don't know who this conjecture is due to, some folklore conjecture perhaps, that if I fix the degree of my number field, and I just, of course, will look at degrees bigger than 2, then most number fields are not monogenic. 100% of number fields are not monogenic. So fix this, then 100% of degree D number fields are not monogenic. And when I say 100%, so I have some kind of way of talking probabilistically about number fields. So here I mean, here's where we order the number fields by discriminant. Or really absolute discriminant. So in other words, I'm saying something like, as I take a limit as x goes to infinity, and I just count k degree D monogenic and discriminant k less than x, degree D. And I just look over all degree D fields of discriminant less than x. That asymptotic, in the limit as x goes to infinity, this should be 0. So 0% should be monogenic. Okay, so that's the conjecture. And as I'll explain, this is open in every degree D for D bigger than 2, for which it applies. To even begin thinking about this conjecture, you presumably have to know something about the denominator here, how many number fields there are of discriminant bounded by x. And even that is, we know very little about that question, but we do know the exact asymptotics for the main term, at least for the denominator here, when D is less than or equal to 5. So at least for D less than or equal to 5, you can imagine trying to say something. And then for D bigger than that, this presumably just, we can't even get started. In particular, we know how to count cubic fields of bounded discriminant. I'm going to just talk about cubic fields for the whole talk, for the rest of the talk. And I'll explain how we know how to count them and so on. But this example here already tells you, we know how to count cubic fields of bounded discriminant, and we know how to impose certain local conditions. These cubic fields comprise, if I did it correctly, 1/12 of all cubic fields. So this example by itself already tells you that at most, 7/8 of cubic fields can be monogenic. So from this very simple local obstruction, you already have progress towards the 100% conjecture. But as far as I know, the only progress towards this conjecture is via local obstructions. The thing is, there are more local obstructions than just this kind of thing, where I demand that locally the ring is monogenic. For cubic fields, the only way that locally the ring is not monogenic, the only way for that to happen is if P is 2 and 2 splits completely, but there are still other local obstructions. So this is what I want to explain. So more general local obstruction. So I want to define the notion of the discriminant of an element. So, well, maybe I should remind what the discriminant of the ring of integers is to begin with. So I write down a basis of my ring of integers. If I want to compute the discriminant, then the discriminant is the determinant of the trace form on this ring, and I can compute it in terms of this basis. So it's the determinant of this 3 by 3, in this case, because now I've started to only talk about cubic fields, 3 by 3 matrix, where I look at the trace form. And this works for any cubic ring that's finite rank, the rank 3 over Z. And so in particular, you can look at the ring generated by any alpha in OK. So if I have an integer, an integer in my cubic field K, then I can consider the discriminant of the ring it generates inside of OK. And it's given by this formula. Of course, here we know a basis. It's 1 alpha alpha squared. So this is trace alpha I alpha j. OK, this is, I'll call this the discriminant of alpha, this thing. And this is, this is some kind of Vandermonde matrix, and we can write it out. So explicitly, it will look something like this: alpha minus alpha prime, where these other alpha prime, alpha double prime, these are Galois conjugates. So images of alpha in some fixed algebraic closure under any embedding of K into that fixed algebraic closure. Okay, but this is an integer, this thing. And according to the way I've defined things, if alpha is an actual integer, then the discriminant is 0, which is a little bit funny, because I've now said that the discriminant of z is 0, but just these are my conventions. And we care about when is this ring the entire ring of integers? So when is this discriminant just equal to that discriminant? And in general, there's this useful formula that the discriminant of the ring generated by alpha, it is the discriminant of OK times the index squared. Where again, if alpha is an integer, then I need to interpret that index as 0. And that's what I'll do. OK. So let's see. Let's try to raise one of these. OK, so what I want then is to come up with an object that keeps track of when I have elements alpha in my ring for which this index is 1. That's what it will mean for the ring to be monogenic. So we just invert this formula. We write down a formula for that index. So we'll define, this is called the index form. So it's going to be a map from OK to Z, and I just send alpha to the square root. This is not really the most elegant way to define this thing, but for our purposes, this is how I want to think about it. This is a cubic form. It's a cubic map on OK. But it's really defined on the quotient, OK mod Z. I mean, certainly anything in Z goes to 0, the way I've defined it, but also Z adjoin alpha plus n is just equal to Z adjoin alpha. So it really is well defined on OK mod Z. This is a rank 2 Z module, and you could expand this out explicitly in terms of some basis, and you'd get a binary cubic form with integral coefficients. So how do I want to write this? If OK, I choose a basis. I can always let 1 be one of my basis elements. So if I choose a basis for OK like this, let's call this map, I don't know, F, capital F, then I can write down a concrete binary cubic form in 2 variables just by setting this equal to this. And what you get is some expression like this, where A, B, C, and D, these are integers. So attached to my cubic field F, I've written down a binary cubic form. It depended on my choice of basis, but if I choose a different basis, then basis of this part of the ring of integers, then that will change the cubic form by the action of GL2Z, the matrix that changes the basis. Okay, and just tautologically, K is monogenic if and only if this cubic form represents 1 or minus 1, but it's a cubic form, so representing minus 1 is the same as representing 1. So K is monogenic if and only if Fk represents 1 or minus 1, same thing, over z. Okay, so this is actually a cubic analog of what Giorgio was talking about. His question was exactly which GL2Z classes of binary quadratic forms represent -1, and now, as we'll see in a second, we're just exactly asking which GL2Z classes, equivalence classes of binary cubic forms represent -1. The arithmetic problem that it turns into is very different in both cases. One case it's norm -1 units. In this case, it has to do with this property of being monogenic. So this is just an exact criterion to determine whether K is monogenic, but we immediately get local obstructions that are new, because if it's monogenic, it needs to represent 1 over z. It therefore better represent 1 over zp for every prime p. So that's the new local obstruction. So if K is going to be monogenic, Fk needs to represent 1 over zp for all primes p for all primes p. Okay, and if not, if there is some prime p for which it doesn't represent 1 over zp, then we say K is obstructed. Locally obstructed, or maybe I might say obstructed at P, and I will also use the terminology locally unobstructed to mean it is, for all primes P, it represents 1 over ZP. And this is a local, it's a local claim or a statement, whether it represents 1 over ZP, and it's easy to figure out which cubic fields have this property, and it's easy to figure out for any fixed prime p, for example, the proportion of cubic fields that have this property. And so it's not easy given the technology that we have in terms of counting cubic fields. And so a fact, which is not too hard to prove nowadays, is that a positive proportion of cubic fields are locally unobstructed. And it's about 75% of cubic fields are locally unobstructed. So you might hope that, oh, maybe 100% of cubic fields are locally obstructed in this sense, and that would prove the conjecture, but it's not true. Most of them are locally unobstructed. They potentially could be monogenic if you only looked at local behavior. Okay, so we'll go over here. So until now, this gives you that around 25% of cubic fields are not monogenic, and that's the extent to which there is progress on that conjecture for cubic fields towards the 100%. But so today I want to explain a sketch of a proof of a theorem with the collaborators that I mentioned, where we go beyond the local, kind of easier local obstructions. So the theorem is simply that a positive proportion of locally unobstructed cubic fields are not monogenic. So we're exactly looking at these cubic fields for which it's not clear whether they're monogenic or not, but we're saying even amongst those locally unobstructed ones, a positive proportion are not monogenic. It should be all of them, should be 100%, but we can just prove a positive proportion, and the actual proportion is very, very tiny. It's around, well, we didn't optimize anything, but it's at least bigger than 10 to the negative 8. But no matter how much we optimize our particular proof, it won't get up to 1%. For example. But we're breaking the barrier to some extent. Well, we're breaking the barrier just the actual proportions are small. Okay, and there's a remark that there is work from a few years ago of Shabnam Akhtari and Bhargava, where they prove this for cubic orders, you can also talk about monogenicity of just subrings of rings of integers in cubic fields. And they prove this exact statement, but where you replace cubic fields with cubic orders. But the method of proof, which is kind of just through 2A equation analysis, all the cubic orders that they're saying anything about are not they're not rings of integers of cubic fields. So they don't end up saying anything about cubic fields. Okay. Any questions on the statement of that first theorem? Okay, I want to give another theorem. This other theorem has to do with thinner families of cubic fields. Historically, when people looked at data, you want to organize cubic fields by discriminant. That's kind of an annoying thing to do. Well, nowadays we can do it fairly quickly on a computer. But the easiest way to do this is to take your favorite cubic fields that you know and understand and only look at those. So for example, you might look at cubic fields that look like this. Or you might look at abelian cubic fields that class field theory tells us exactly what they are and how to write them all down. And so here's a more general kind of thing that you could do, more general class of thin families of cubic fields. So I'm going to let F be either a quadratic field, or I'll also allow F to be Q, which I'm thinking of as the split quadratic algebra, Q cross Q, but yeah. And okay, a definition. So K is always a cubic field here. So a cubic field K has resolvent or quadratic resolvent. This is a very old term. F, if the discriminant of K agrees mod squares with the discriminant of F. For every fundamental discriminant, you have exactly one of these Fs. And cubic fields don't have to have square-free discriminant, but here I'm saying that its square-free part agrees with, or its fundamental part agrees with F. So mod, let's say Q cross squared. This is a very classical notion because this comes up when you solve the cubic in Cardano's formula. And so another way to say it is F is the unique quadratic, at least if F is not Q, which is one slightly annoying case. Another way of saying that K has resolvent F is saying that F is the unique quadratic field in the Galois closure of K, and that just follows immediately from that expression for the discriminant. Those roots all live in the Galois closure. You square root it, you get the discriminant. You square it, you get the discriminant. Okay, and so what we'll do is we'll now look at families where you fix F, and you look at all cubic fields with quadratic resolvent F. Maybe I should just give two examples, which will be helpful. Okay, let's move this one over down. Oh. Okay, it's not. Say that again? Where is the form up there? So it's exactly the discriminant of the field. Yeah, so I'll talk about that in a second. Just didn't see who asked the question, but yeah. Okay, just an example of this definition. If F is Q adjoin root -3, then K is of this form, pure cubic fields. So if your cubic field has resolvent this particular quadratic field, then that means you're a pure cubic. One implication is, or the other way is clear. If the Galois closure of this, of course, contains this field, because it contains a third root of unity. but it's if and only if. And this case where f is q, this is exactly saying k is Galois, or abelian even. It's with Galois group C3. That's discriminant being a square is saying it's Galois in this case. So this is just a generalization. I mean, people focused a lot on these two families because these families we understand. You can compute, look at rings of integers, and ask whether it's monogenic. So now I want to give a theorem where we just do this in general. So let's fix f as before. And the first part of the theorem says that once I fix f, 100% of cubic fields are not monogenic. So 100% of cubic fields with resolvent f are, well, it's not even just that they're not monogenic, they're locally obstructed already. So are locally obstructed. And in particular, not monogenic. So when you look in these families, without doing anything particularly fancy or hard, you actually can show that 100% are locally obstructed, just for local reasons. So it's natural then to ask, okay, it's already true that 0% are monogenic, but you can ask about that thin set of cubic fields which are locally unobstructed. It's 0%, but it's still asymptotically, there are still a lot of them in some sense. You can ask, what about those? And again, the answer is 100% are not monogenic. So here we do need to, our method of proof doesn't work when we're in that case of abelian cubic. So if f is not q, or it works, but it just doesn't give us an answer, it's not strong enough, then 100% of locally, or let's say unobstructed cubic fields with resolvent f are not monogenic. So even amongst even within this thin set of cubic fields, which are locally unobstructed, 100% are not monogenic. Okay. So, yeah, I mean, the picture I like to draw is, this is how I think of cubic fields. I have a cubic field that has, its discriminant is the discriminant of its resolvent times some n squared. Maybe we'll call this d n squared, where d is a fundamental discriminant. And so you have two axes. You have the fundamental discriminant axis, and then you have the n axis. And so here is q adjoin root 5, q adjoin root -3. And the first theorem is talking about the whole space, and it's saying that within this whole space, a positive proportion of unobstructed cubics are not monogenic. The second theorem is looking at vertical lines that cover the entire space. And it says on each vertical line, something much stronger is true, that 100% of these cubic fields are not monogenic, even if you only look at those unobstructed ones. But things are weird in this kind of picture. For example, you could look at n equals 1. And then look at this cross-section of cubic fields. At any one point here, you might have more than one cubic field here. There's only finitely many, and you might have 0, but you might also have more than one. So if you just look at this cross-section, you're exactly looking at the set of all cubic fields of fundamental discriminant, and that is a positive proportion of all cubic fields. So fundamental discriminant cubic fields. But this theorem tells you absolutely nothing. It's totally clear that this theorem tells you absolutely nothing about this positive proportion of cubic fields, because this is a finite set of points in every vertical line. I can throw them out, and my asymptotic results don't care. And so this seems to be indicating that the conjecture has good evidence for the conjecture, but it's also missing a lot. It's also not telling you anything about these fundamental cubic fields. And so our theorem one, the strategy of the theorem, it uses powers of squares, or it uses squares in the discriminant to get going, and so it actually says nothing about these fundamental discriminant cubic fields. So there's some relationship between the strategy in that theorem and what's going on in this theorem.
So you said when you fix the quadratic leisure bond, 100% of number field is non-monogenic.
Yeah.
Can you give the quantitative
Yeah.
value for monogenic field?
For monogenic?
Yeah.
That we just have some upper bound. We don't know like a.
Yeah, upper bound.
So this is all quantitative. The funny thing is that the exact asymptotics actually depend on the field. Even the main term, this field is funny. This field has more cubic fields than others, and so I didn't want to. I'd have to like break it up into cases to write down things asymptotically. And I also only care kind of qualitatively for this talk. But yeah, we have asymptotics. We can't pin down the number of monogenic cubic fields in one of these families, but we have an upper bound, and yeah. Okay. Other questions? Okay, so I'm going to talk about the proof. The proof goes through rational points on elliptic curves and statements about average ranks, Mordell-Weil ranks, and families of elliptic curves, which maybe seems out of nowhere. I won't be able to talk about this one of the key ingredients in the proof, so I just want to state it as a theorem in its own right. It's interesting in its own right. So if I have time, I'll talk about it, but I don't think I'll have time, so I'll just state it. This is actually an ingredient in the second theorem, which is in some sense the harder theorem of these two, as it turns out. And so we're going to look at a family of elliptic curves here. So let's fix D, which you're supposed to think of as being this D. So it's like I fixed the quadratic resolvent. And then let's let EM be the elliptic curve x cubed plus dm squared. M is an integer. Might as well let it be positive. So this is a cubic twist family of elliptic curves, not a quadratic twist family, a cubic twist family. And the statement, well, we have the theorem of Mordell and Weil, or just Mordell in this case, that the group of rational points is finitely generated. So this is z to the rank em, direct sum some torsion group. This torsion group is generally trivial in these families, so we can safely ignore it when we talk about average questions. And the theorem is that the average, well, there's a consequence towards the average rank, but maybe I'll state it like this, that the average size of 2 to the rank is less than or equal to 3. And so in particular, the average rank you can deduce from this is at most 1.5. So you have many, many curves of rank 0 or 1, for example, in this family. So this is an open question, whether in this family you have boundedness of average rank. And so we're going to use this as input into this theorem. There's a similar theorem that gets used as input to the first theorem. It's just it was already known. We proved a similar theorem for the sextic twist family earlier. And I should say this theorem, when d equals 1, is really due to Alpoj already. There's a nice space in which you can count what are called 2 Selmer elements when d equals 1. When d is not 1, there isn't such a space, and so we had to do something else. Or we'll use his result, but there's some trick, basically. Okay, I don't think I'll have time to talk more about it, but you can ask questions at the end. Okay, so I'll start the sketch of the proof unless there are questions. Let's just go here, no? Nope. Okay. Okay, so, oops. Okay, so we'll just think about Theorem 1. So there are three main ingredients, but before we give kind of an interesting ingredient, we need to just talk about how we're counting things to begin with. As I said, we need to know how to count cubic fields to begin with of bounded discriminant. So we use this bijection. People call this the Delaune-Fadiev bijection. There are other names associated to it. It says that cubic rings, so rank 3 rings over Z, are isomorphism classes of such things are in bijection with orbits of binary cubic forms. So we look at integral binary cubic forms, and we look modulo a GL2Z action by transformation of variable. There's a little determinant twist, but I won't worry about it. And the bijection is exactly what I already wrote down. You just send a ring R to this index form. And this is kind of an amazing thing, that the index form exactly tells you, tells you the original cubic field. It's not a hard bijection to prove. It's not a hard theorem to show that these are bijective. So here I've written R as Z plus Z omega Z theta. And the important thing about this bijection is it's not an arbitrary bijection. There's a lot of rich properties of the ring here get translated into properties of the form here, and in particular, discriminants match up, as was asked already. So the discriminant of R is the discriminant of FR. But it's more than that. There's some rich arithmetic structure being transferred by this bijection. And this is what Davenport and Heilbronn used to count cubic fields of bounded discriminant. If you want to count cubic fields of bounded discriminant, it amounts to counting orbits of these lattice points sitting inside of a 4-dimensional vector space modulo a group action, and this is what they did. So Davenport and Heilbronn showed that the number of cubic fields of bounded discriminant, this is some explicit constant times x plus some little o of x term. They get some error term, and this constant is a zeta value, 1 over zeta of 3, roughly, explicit constant. Okay, so this is how we can count cubic fields to begin with, and for us it's very nice that the object that will tell us whether a cubic field is monogenic or not is exactly the thing that we're counting with to begin with. So that's very, very helpful. But okay, how do we get going? How do we say anything about monogenic cubic fields? So what we do is we start thinking about integral points, really, on a certain elliptic curve, certain family of elliptic curves. So suppose K is monogenic. Let's say it has discriminant D. Well, what does that mean? As we've said, that means that the corresponding form F sub K, I forgot if I called it F sub K, but we'll call it F sub K, corresponding to the ring of integers here of K, it represents 1. So this means that F sub K, which I'll write it in terms of its 4 coefficients, this represents 1 over Z. What does that mean? If you think about this, it means that A, I'm allowed to change my basis potentially, and A can be 1. So this means that A is 1. And I have a monic cubic form. Now I complete the cube, so send x to x minus by over 3. Is that what it is? Yeah. complete the cube, kill the b term. So that means that I can write f as x cubed plus ax y squared plus b y cubed. A and b, I guess, could have some 3's in their denominators, but not too bad. This is now, the fact that this has discriminant d, we can write down the discriminant of this form, and we have a solution to the equation. So we get an integral point on a certain elliptic curve, because d is minus 4a cubed minus 27b squared. And so I got an integral point on the elliptic curve, minus 27y squared equals 4x cubed plus d. And I want to, like I said, it's not quite integral actually. There are these 3's in the denominator. So I'll change the model of the elliptic curve. And then that will actually give it a much nicer form anyways. And then I will have an actual integral point on the elliptic curve. So you get a point, get an actual integral point, not just like a 3 integral point. We'll call it p sub k on the elliptic curve ED with equation y squared equals x cubed minus 432 times d. These are isomorphic elliptic curves. It's a different model. And in this model, these points are integral points, integral coefficients. Okay, and now I'm going to write, we're going to study these integral points that we just constructed. So I'm going to let E dz of max be the set of integral points that arise from this construction. And it's important that we're not getting all integral points. So for every monogenic cubic field, I've constructed an integral point. In principle, I actually could have constructed several of them because there might be other ways to represent one with the same form, but I don't really care so much about that. I at least have one for every monogenic cubic field. And I'm looking at the set of all integral points that could arise from such a construction, from like monogenic K. And what we'll do is we'll study the following map. We'll look at, and this sits inside the set of all integral points, sits inside the set of all rational points. This is a group. We can mod out by 2. And I'm going to consider this composition. People who study integral points on elliptic curves do this all the time, and they study this map extensively. And this is when you try to study the integral points on this family. This is like one of the most famous families of elliptic curves, especially for integral points. You worry about the fibers of this map. The fibers of this map can get very big as d gets big. And what's going to make our theorem work is that when I look at these special points, these max points, max for maximal order, the fibers are not big. They're absolutely bounded, independent of everything. So that's the first main ingredient. Okay. Nope. A little over 5. Okay. Oops. Okay, so the first ingredient in the proof of our theorem, I don't know, I'll call it ingredient A, is that the fibers of phi d are absolutely bounded. In size. So independent of d, independent of the choice of point in here, which is just a constant which bounds the size of all such fibers. Okay, so that's the first ingredient. I'll say the ingredients, and then if I have time at the end, I'll say a little bit about how you prove it. This is the thing I really wanted to talk about, this ingredient A. On the other hand, this group here, I mean, we've bounded the size of the fibers here, and then here we can bound by a result of the type that I wrote over there. For that was a cubic twist family. For us, in this case, we'll use a result of Levint's for the sextic twist family. But maybe I'll say first, so ED of Q mod 2ED of Q. Just so that I can formulate his result in a clean, nice way, because it's stronger than just bounding the size of this. He actually computes the exact average size of the Selmer group. So there's this whole notion of descent, which I don't want to get into, but this group, which in principle is kind of a hard thing to compute, lives inside a slightly bigger finite group that you can compute. And this, you compute it in terms of orbits of binary quartic forms. Okay, I won't define it or even talk about the quartic forms, I guess, but the second ingredient, if you know about Selmer groups, then you know what this is. The second ingredient is that this is a theorem of Levint, which says that the average size of the 2 Selmer group in this family is exactly equal to 3. And it's important here, so for any nice set S and Z, the average, I won't write this down rigorously, where you just average only over those D in S of the size of the Selmer group is exactly equal to 3, and then from this you get a bound on, because of this inclusion, you get a bound on the size of this. Nice here means you are allowed to impose certain congruence conditions, including some infinite families of congruence conditions on S, and I won't say it in detail. Okay, the upshot of these two ingredients together is that we can bound the total number of potential monogenic cubic fields on average, and it's O of X. There are O of X of them. That's what you get. There's an absolute bound here, and then there are, O of X with D less than X things here, and so you get an O of X bound. The problem is that if you write it out explicitly, you see what that constant is. It is way bigger than the number of cubic fields, period, total. And so this by itself does not say anything about monogenic cubic fields. So there's a third ingredient that we need, and this has to do, I wanted to just say, the proof here is a circle method proof. It goes via the circle method, but I won't say more on that. And I should also say, when you look at all integers, there is a result of Ruth, a PhD student of Bhargava that was never published, where he does this. But we absolutely will need this for some general nice sets S. Okay. So the third ingredient has to do with understanding the set of discriminants that arise as the set of integers that arise as discriminants of cubic fields. So I said Davenport and Halbrand showed it's O of X. So you might imagine if you go through all numbers up to X that it's roughly uniformly distributed or something which discriminants show up. But what actually happens is that it's very choppy. There are lots and lots of integers that don't show up as discriminants of cubic fields at all. It's actually a very thin set of integers that will show up. Well, no, not precisely thin, but just not very many in some sense. But then when discriminants do show up, they show up in huge clumps. And we're gonna take advantage of that. And so here's what we'll need for the third ingredient. We're gonna find a nice set S with the two following properties. First of all, that there are many cubic fields per discriminant in S. With discriminant in S. Many meaning many more than the density of the set S within integers up to X itself. That's the first condition. And the point is that since this doesn't care about S, we'll get lots of cubic fields, even though the average stays the same. So that's the point. And then the other thing we need is of course, to prove our actual theorem, we need to make sure that we're looking at unobstructed cubic fields. So you also want to arrange for any cubic field with discriminant in S, you want it to be unobstructed, so that we know that we're always looking at things that will help us prove our theorem, cubic fields that will help us prove our theorem. Okay, and I'll just give you an example of the kind of sets we use. Okay, let's just go. Okay, thanks. Whoops. So I'll just write down the kind of set that we use, and then I will have to stop shortly after that. So an example of such a set would be fix an integer m, which is a product of a bunch of primes, t primes, all of them 2 mod 3. And just look at the set of integers, which are fundamental discriminants times that integer squared with d fundamental discriminants, so essentially square free, and with various Legendre symbol constraints. So what do I want to write? D over pi equals -1 for all pi. So if I let the number of factors be really big, this is a very thin set. The density of the set of integers gets thinner and thinner because I'm imposing these congruence conditions. On the other hand, you can show that you have tons of cubic fields per discriminant in the set, and it's because there are no cubic fields that have discriminant that violate this congruence condition. So when you sieved out those discriminants, you actually didn't throw out any cubic fields at all. And so this is how you arrange to do this, and the 2 mod 3 will just tell you right away that they're unobstructed for easy reasons. When you combine these 3 ingredients, you get theorem 1 because we can choose t to be as big as we want. I don't even need to know the absolute bound on the size of the fibers. As long as I choose t to be big enough, then the density will grow. Okay, so I'll stop there. Thank you.
Thank you. Are there some questions, comments? No.
Is there a conjecture, at least for if you fix the resolvent, how many of the fields above that should be monogenic, like there is overall?
If you fix the quadratic resolvent?
Yeah.
You mean an asymptotic density?
Yeah.
I think we have, we have a guess for what it is. It's something like x over some fractional power of log x or something. I could tell you, but or really x to the 1/2 if you're caring about the actual discriminant.
Okay. Well, then a kind of naive follow-up. If you add those up blindly, do you get what the expected conjecture is?
Yeah, so the answer is absolutely not. Even in Davenport Heilbronn, you can count. I didn't talk about how you count cubic fields with fixed quadratic resolvent, but that's something that you can do. I did this in a paper with Manjul. You can then add up all the counts and see if you get the number of cubic fields, and you absolutely do not. The error terms overflow, and yeah, so you will never be able to say anything that way.
Cool,
yeah.
Thanks.
Other questions? Thank you again.
Thanks.